Welcome, my name is Terry Soul, and this is Programming Chaos, a channel devoted to fun and interesting programming projects to help you hone your programming skills. Today's project is a technique known as spatial partitioning, and it is used to get enormous speed up out of multi-agent simulations. So things like particle life, where you have tens of thousands of particles moving around and interacting, you can use spatial partitioning to make it run much, much faster. Or if you're doing an artificial life simulation with lots of interacting organisms, or maybe a large-scale combat game with tens of thousands of troops, anytime you have lots of agents that need to interact with each other, you need to pick some algorithm to get things to run much faster. Spatial partitioning is one of the simplest and most effective ones as long as some basic conditions are met. And for spatial partitioning to be effective, the condition is that there is a maximum distance on your interactions. So for example, if you're familiar with particle life, there's a maximum distance at which forces are applied between two particles. As long as they're closer than that max distance, they interact. If they're further apart, they ignore each other. Same thing if you have, say, a maximum sensing distance, and you know that organisms or troops in a battlefield cannot see each other if they're more than some distance apart, then spatial partitioning is very simple and very effective to speed up your simulation or your model. So in order to understand all of this a little better, I'm going to start with some code that I've already written that basically does things the stupid way. So the goal of this code is to take a bunch of particles and simply draw lines between any that are within a max distance, in this case 100 pixels of each other. So here's the code. I have a world, and then I create an array list that I'm going to put my particles into, and a maximum number of particles happens to be 2000, and my maximum distance that I want to draw a line between them if they're within that distance apart. I've got some ability to zoom and move around, so some camera controls that we can ignore. Setup code is pretty straightforward. I create a window. Again, the offsets are for moving my image around a little bit with the camera. I'll show that in a minute. But then I just create an array list of particles, and I add new particles to that list. And again, in this case, I'm adding 2000 particles. I want to print the frame rate, so I've got a little bit of stuff for the text size. And then the main draw loop is fairly typical. I'm zeroing out the background, so filling it in all black. I'm gonna do a little bit of translating. That's my moving the camera around. And then I simply go through that whole swarm, ask each particle to update itself, and then display itself. And then at the end, I put in the frame rate. The code down here, if you're interested, is again for sort of moving my image around. So I can drag the frame around and I can zoom in and zoom out. And then if we look at the particles, each particle object has a position. And when I create a new particle, I just give it a random position within the size of the whole world, which is quite a bit bigger than the window. There's a display function, so I display each particle. And you might notice I'm displaying them as a rectangle rather than a circle. The default is often to draw things as a circle. Turns out that's about half as fast as drawing rectangles, because to draw a circle, we don't have to do it, but the code internally does a bunch of calculations to make a nice smooth circle. Rectangles are a lot faster to draw. So a minor hint there for speeding things up at least a little bit. The main part of the particle class is the update function. And so what that does is for each particle, it goes through the entire swarm. And as long as the particle that it's looking at is not this particle, I don't want to draw a line from a particle to itself, then we calculate the distance between them. If that distance is less than the maximum distance, we draw a line between them. So like I said, this just takes all of the particles, and if they're within 100 pixels of each other, it draws a line between them. And it is very inefficient because if I go back to my main code here, every single particle has to check against every other particle. And so if I have 2000 particles, that's 2000 times 2000 checks. Or more abstractly, that's n squared checks, where n is the number of particles. And so if n increases by a little bit, n squared increases by a lot, right? We've got this hideous curve. And that's what makes, in this simple / stupid version of the code, it's so difficult to have lots of agents or lots of particles, because the speed goes up as the square of the number of particles. And we can see that if I run this, my frame rate is 60, which is pretty good. Here's my zoom and move around. Turns out there aren't very many particles that are close together, and so not very many lines being drawn, and I can zoom out and they're sort of the whole world. Nice frame rate, no problem. But if I come in and say, well, I want to change the number of particles from, say, 2,000 to 6,000, notice what happens to my frame rate. It drops significantly, and that's only 3 times as many particles. One of the interesting things is the frame rate tends to drop a little bit right at the beginning, and I believe the reason for that is processing calculates the frame rate over an average window, and it starts by assuming the frame rate is 60, which sort of throws off the average. So it takes a little while for it to bring the average from 60 down to the true frame rate. But there we go. So not even a very big increase in the number of particles, and my frame rate is tanked. And the reason, again, is I'm doing n squared comparisons. The way that we fix this, well, there are lots of different ways to fix it. So a few of the possibilities include things like quad trees, KD trees, spatial hashing, or the one that I want to talk about, which is spatial partitioning. And again, spatial partitioning works really well and is relatively simple to code as long as we're dealing with some maximum distance. That's the key. So if we had a different kind of model, for example, we had a model where particles interact with the closest neighbor no matter how far away it is. So one particle might interact with another particle, even if it's on the other side of the world, as long as it's the closest one. There's no maximum interaction range. Then we'd have to do something like a quad tree. But as long as we are dealing with a max sensing range or a maximum interaction range, spatial partitioning is often even more efficient and certainly simpler to code and understand. So let's see how spatial partitioning works. Okay, so here's a zoomed in image, and let's imagine I'm dealing with this particle, and what I want to do is find all of the neighbors within that maximum distance. I think I was using 100 pixels, and draw a line between them. So the key is particles that are far away, I clearly don't need to worry about. So instead of creating one long array list of all of the particles, what I want to do is add a grid, and each grid cell will contain a list of the particles only within that cell. So for example, for this cell right here, it will have its own array list with 3 particles in it. Or here I have a cell that will have an empty array list in it. The key to making all of this work is the size of each grid cell is equal to that maximum sensing distance. So this radius and this distance is the same. And the reason that works is, let's consider this particle again. I need to consider all of the particles that are within its cell, but also all of the particles that are 1 cell away in any direction. So for example, for this particle, these 2 particles are within 100, even though they're not in the same cell. But a particle over here cannot be within that maximum distance, right? Because the width of this cell is the maximum distance. And so the only way that this particle, an imaginary particle right here, could be within my maximum distance is if this particle is in this cell. And if the particle is in this cell, then I don't have to worry about looking at those anymore. So the idea is, for a given particle, we simply look at all of the particles that are within 1 cell of it. So instead of the whole world, I'm always limited to just this area. And that means that the size of the world doesn't matter, right? I can make an arbitrarily large world, but I only ever have to check the 9 surrounding grid cells. So in terms of the code, instead of having one array list that stores all of the particles, I have a two-dimensional array of array lists, and each cell has, as I said, its own array list that stores the particles in that cell. This is the standard sort of basic way of doing spatial partitioning. It turns out you can get a little more sophisticated if you have different types of particles with different maximum ranges. So for example, if I had some particles whose maximum range was between 0 and 100, and other particles whose maximum range went all the way up to 200, I could still, for example, make my grid cells 100 by 100, and some of the particles would only look at one neighbor away. But then the particles that could sense further, that could sense out to 200, I'd simply expand the range of the cells they have to look at. And so you can, this is a sort of a more flexible way of doing spatial partitioning. You can say, well, my grid cells are 100 by 100, but then based on the sensing distance of this particle, I can decide, do I only have to look one away because their max sensing range is 100 or less, or do I have to look two away because their sensing range is, say, 180, so I've got to look a little further. This gives you a little more flexibility in terms of having particles or agents whose sensing ranges are larger or smaller. A little more of a complicated idea. Adding that will make sense once we look at the code. So in fact, let's do that. Let's go ahead and start writing up the code for doing spatial partitioning. I'm going to start with my old sort of dumb code and, if you will, make it smarter. Okay, so let's see spatial partitioning in the code. So I have here my old, as I said, sort of simple but stupid approach, and I want to turn it into a spatial partitioning approach. And the first thing, as I said, instead of a single array list of particles, I need a grid of array lists. And I'll call that swarms. And what I'm going to do is comment out the old version just so that you can see that sort of as a reference. So again, instead of a single array list, I'm going to have a grid of array lists. And then I still want a bunch of particles. I'll go back to the 2000 I had before to start with. I have my max distance, but now I need some information about this grid. So I need to know the size of each cell in the grid, and that of course should be the same as the max distance. So I don't really need two variables, but I think it's a little easier to understand if I have them both. And then I need to know how wide and how high the grid is, so that I can loop over all of the cells in the grid easily. And then I can go into my setup, and of course I don't have a swarm anymore, so I'm gonna comment out all of that code. And instead what I need to do is create my new array or grid, if you will, of array lists. So the first thing I need to know is that grid width and height. So the number of grid cells I have in width, that is the number, if you will, of columns of grid cells, is just the world width divided by the grid size. And one thing I did here to make life a little easier is those all divide evenly. So the world width is 8,000. My grid size is equal to my max distance of 100. So I'm basically going to have 80 grid cells wide. If those don't divide out evenly, you have to be a little bit careful to make sure you have an extra grid cell on the end so you don't get overflow errors. So easier to make them divide out nicely and symmetrically. And then I do the same thing for the grid height. And now I can create my swarms. And this is one that always trips me up if I'm not careful. Two-dimensional arrays are rows, and the number of rows is actually the height by columns, and the number of columns is actually the width. So I always want this to be the x value, which is the width, but it's not. It's the number of rows, and therefore it's the height. And now I have to go into that array and put an array list into each element of the array. So this is going to go through each row starting from 0 and going through the height of my grid, and then I have to go through each column and create my new array lists. One of the tricks that I use is, in this case, my variables for my for loops are R for rows and C for columns, and that makes it easier for me to remember to put row first and column second. So that goes in and creates my grid or my two-dimensional array of array lists. And then I simply need to put in a bunch of particles. It's worth noting, this is how I created a single array list before. This is now the equivalent code to create my grid of array lists. And this is the for loop that I've used before to add my new particles. This will be the new for loop here. So I'm going to create the same number of particles, but now I have to make sure to put them into the right array list. So create a new particle and put it in the right cell. So what I'm doing is taking the Y position, because the first argument is the row, and dividing it by the grid size. And that will tell me which cell it should be in. And then because this is an array, of course, I have to turn it into an integer. And then I'm going to do the same thing for the X value. So that tells me which grid the particle should go in, and then I simply add it. There we go. So a little more complicated than adding each new particle to my single swarm. I've got to add each new particle to the right grid cell, the one that it's currently in. In terms of updating and drawing the particles, I'm going to borrow these nested loops again. So I'm going to copy that and come down to my draw code. So I'll comment this out and replace it with my nested for loops. So this is going to go over every single grid. But of course, I don't want to create new array lists. What I want to do is display every particle in that grid cell. So this ends up being for each particle in that particular grid, I simply need to display it. So go to each grid cell, go through each particle in that cell, display that particle. And as long as I'm here, I'll also put in the update. And now I have to change the update in the particle class. So here, of course, I'm getting an error right away because the update is trying to go through the swarm that doesn't exist anymore. So let me comment out this version and I'll put in the new version. So the trick here is I know the location of the particle, which means I know which cell it's in, but I need to compare it not only to the particles in its cell, but also to the neighboring ones within a particular range. So I'll start by putting in a range, and I'll just make my range 1. So I'm just going to look at one neighbor. But as I said before, you could look at the sensing distance or the interaction distance for this particle and compare it to the cell size and say, well, actually, I need to go 2 cells over or 3 cells over. And so the range would be a little bit different. But we'll just do the standard 1 to begin with. And then I need to know which cell this particular particle is in. So basically, the row that it's in is its Y position divided by the grid size. And similarly, the column that it's in is its X position divided by the grid size. And now I just need to look at all of the grid cells, the one it's in plus all of the neighboring ones. So this is my delta X. I guess I could have used delta R instead. So it's shifting over by 1 row. And then the same thing, I need to shift in the Y direction. So actually the Y should be the rows, X should be the columns. So for X, I could have used DC for the delta column and DR for the delta row. And so now I need to know the new grid cell. So the grid cell that I want to look at I'll call it the grid row, is the row plus, and I immediately got it wrong, dy, because I'm shifting either up a row or down a row. And the problem here is if my particle is in row 0 and I shift up by 1, that's going to put me in row -1, which doesn't exist. Depending on whether or not my world wraps around, I might actually want to wrap all the way around. And so to fix this, I'll do the following. I'll take the row that I'm in after it's been adjusted, add in the total height, and do a modulus of the height. And that basically automatically wraps. So if my particle was in row 0, when I subtracted 1 from it, that would put me in row -1. If I add the grid height, that takes me all the way around to the last row. And if I did the opposite, if I was in the last row and I added 1 to go outside the bounds, doing the modulus takes me all the way back to the first row. So this makes sure that my new row is within the right range by wrapping. And then I can do the same thing for my columns. And then I'll make sure that I'm within the proper bounds. So what this is doing is it's saying, I know what grid cell my particle is in, and I'm just doing a delta. So I'm checking all of the cells around it. And to check all of the particles within that, I'm going to use actually the same sort of for loop that I had right here. Except, of course, instead of going over the whole swarm, I'm just going over the list of particles in that particular cell. And I'm going to put in a check to make sure that I'm not comparing the current particle is not the same as the particle I'm comparing it to. It absolutely doesn't matter in this case for drawing lines, but if, for example, I was doing a particle life model where I was calculating the forces between particles, you don't want to calculate the force between a particle and itself because the distance is 0, and that typically means the force is undefined. Same thing, if you have organisms that are sensing each other, you probably don't want organism to be sensing and responding to itself. It doesn't matter for just drawing lines, but it's good to keep in mind that you want that. Don't check a particle against itself most of the time. And then the rest of the code is basically the same. I'm going to calculate the distance between the position of the current particle and the particle P that I'm comparing it to. And if D is less than the max distance, I'm going to, and I put this comment in below, I'll put it here too, I'm going to do things. And those things could be calculating forces, or in an artificial life model, it might be chasing down the prey that you've just detected, whatever things that need to happen if they're within that maximum distance. Of course, in my case, it is just drawing a line. So I'm just drawing the line between this particle's position and the other particle P's position, where P is in the list of the grid cell that I'm looking at. And now I need a bunch of closing curly brackets here. I think that's all of them. If I haven't made any typos, let's see how this works. So there we go. Nice high frame rate, which is not a surprise because I'm still only dealing with 2,000 particles. So no real change. Let's go in and change this to, scroll back up here, 6,000 particles. Well, now instead of my frame rate dropping off, it is still right up there at about 60. One of the things you'll notice if I zoom out a bit, it starts to drop, not because the number of particles has changed, but because the number of particles being drawn. So it's no longer, the bottleneck isn't the interactions. The bottleneck here actually becomes simply the display pipeline. And in fact, if I were to up this further, so instead of 60, let's go to 20,000. So 10 times as many particles as we had before. My frame rate is not bad. It's about 30. If I zoom out, it drops quite a bit, but not because of all of those interactions. It's dropping because of all of the drawings that have to be done. And in fact, you can see that if I go in here and I'll comment out the lines, I'll just draw the particles. Now my frame rate stays at about 60 regardless. So the bottleneck again was not the comparisons, but it was simply the drawing. Another factor that makes a difference is as I add more particles without expanding the size of the world, there are more interactions. So within that 9 by 9 grid, there's a lot more particles that are interacting with each other. If I were to expand the size of the world so that the density remained the same, I also would have a much smaller fall off in terms of the frame rate. So this is a huge difference, right? In my old dumb version, even at 6,000 particles, things were starting to get impossibly slow. Now I can jump to 20,000 particles and I have a perfectly good frame rate. If I were to increase the size of the world, so I'm going to make my world much bigger to reduce the number of interactions. Now my frame rate is pegged right up there at 60. Now I can go in and let's jump up to say 60,000 particles. Still a very good frame rate. Now, if I were to draw the lines back in, it would probably fall off again. But the limitation is no longer the number of particles and calculating the interactions between them. It's actually just the drawing pipeline. That suggests one other improvement that I often do in my simulations, especially if I'm doing something long-term like evolutionary particle life. I'll put in an option to turn off the graphics so that it is doing the simulation in the background, and usually it's set up to be like the D key for display or don't display. If I want to allow something to evolve overnight, I'll turn off the display because that improves the frame rate and the speed significantly, right? So there we go, 60,000 particles. And we could probably push this quite a bit higher, 120,000. Okay, a little bit of a fall off in the frame rate, but still not too bad. As opposed to without the spatial partitioning, I couldn't go to 6,000 particles. So an enormous difference. Again, I think I mentioned this twice already. The key to using spatial partitioning is that you have that maximum interaction distance. And as long as you have a maximum interaction distance, this is a fantastic way to vastly improve your efficiency. If you don't have a maximum interaction distance, if you have particles that can interact at an unlimited distance, then you need to take a different approach like a quad tree. So there is a major issue that I've been overlooking so far, which is what happens if the particles are moving. So updating the particle position is not hard at all. The problem is when the position updates, a particle may move from one grid cell to another grid cell. And so we have to update which array list they're located in. Let's take a look at how to do that. And the first thing I need to do is to get the particles to actually move. And I'm just going to do that with a random motion. So let me go back to my particles here. And I have my update function. I will put my lines back in. Why not? And I'm just going to say each particle after I do the update, I'm going to give it some random movement. Typically that might be done in here where if two particles were less than the max distance apart, we'd apply some forces between them in say a particle life model, or maybe we'd have them move and orient on each other in a predator-prey model. I'm not going to mess with any of that. I'm just going to add some random movement down here at the end of the update. I need a new position, which is a copy of the old position. And I don't just want to change the position itself because this is the update. And if I were to move one of the particles, that would change the calculations for all of the other particles. So I sort of want to calculate how they should move as part of the update, and then as a separate step, have them all simultaneously move. So this is the new position basically for the next frame. And I'm getting an error because I haven't defined it. I'm going to make it part of the class. So I'm just going to come up here and say I need another p vector, which is my new position. And then in the constructor, I need to create it. And it doesn't matter where it starts, so I'll just set it to 0, 0. So my new position is going to be a copy of my old position. And then I'm just going to add a random two-dimensional p-vector to it. So this is a built-in function as part of the p-vector class. And now I do need to make sure that that doesn't cause it to go outside the bounds of the world. So I'll put in some checks for that. There. So I've got a new position, which is just the old position plus a random vector. And then I'm doing some checks to make sure that it stays within the bounds of the world. And really this is wrapping around. Now I need to do two things. In a separate loop, I need to go through and update all of the positions so that all of the particles move simultaneously. And at the same time, really in the same loop, I need to update which grid cell they're in if they have moved far enough to change grid cells. And I'm going to do all of that in my main draw loop. So let's come over here to the draw loop. So this is the piece where I'm going through each grid cell, and then I'm going through each particle in each grid cell and updating their position. And I also happen to be displaying them. Now I need to do something very similar, but I need to move them all, change their position, and also potentially change what grid cell they're in. So the first thing I'm going to need are some variables for the new grid cell they're in. So that's just a new row and a new column. And then I have to go through every particle in every grid cell, so I can copy these two loops. I also need to go through every particle. But when I go through the particles, I might be removing them from the current array list and putting them into a different array list in a different grid cell. So I can't use this style of for loop. If you're going to remove something from an array list, you have to start at the tail of the array list and work backwards, like this. So start at the end of the array list and work back to the beginning. And to do that, I have to grab the particles. So now that I have the particle, what I need to do is calculate the new grid cell that it might be in. It might stay in the old one, but I've got to calculate what it is based on its new position. So the new row is the Y part of the new position divided by the grid size, and then the same thing for the new column. And now I just need to check whether that's actually changed. So is that new row different from the old row, or is the new column different from the old column? And if it is, then I need to move my particle. So remove it from the old array list and add it to the new array list. And then the last thing I need to do is update the position. So now it's potentially in a new array list and it's definitely moved to a new position. Close my for loops. And from a technical perspective, instead of displaying the particle here, maybe you want to display it at its new position. That's up to you. Minor difference in terms of sort of which frame is it being displayed on. So if there's no typos, again, this should run. There we go, out of bounds. Let's see if we can fix that. Of course, always make this mistake. I put in a plus plus, should be a minus minus. I'm going the wrong way through the array list. There we go. So this was with my very large numbers of particles and my very large map. So we're not seeing very many connected lines. So let's change those parameters. I'm going to make my map smaller. And just in the interest of time, I'll just go with 12,000 particles. So now we can see lots of particles sort of densely connected. And you'll notice the lines appear and then disappear as the particles move around. It's just sort of a vibration because it's just random noise. But what that shows us is that they're correctly moving in and out of different grid cells. And in fact, not a bad thing to do if you want to see this is you can actually draw the cells in just by drawing some rectangles of the proper grid size. So let's see, where is my grid size? Right here, the max distance. So a bunch of 100 by 100 cells, and then you can sort of see them as they shift between cells. Not really critical for this. The main point is, sure enough, my particles are moving, but they're correctly updating what cell they're in so that they can correctly update what particles should be connected. So there we go. Now we can handle our movement as well. The key point, which I think I've said twice already, but bears repeating, is spatial partitioning works really well as long as you have a maximum interaction distance that you can use as the max distance and the grid size. And of course, there are other improvements that could be made. We could do all of this in a shader code, for example, and then it would run even faster. We could figure out ways to parallelize it. But as a first step, spatial partitioning, as we've seen, gives an enormous speed up and makes lots of simulations possible that otherwise would just be sort of too small to be interesting. Okay, thank you for watching and happy coding.